not only the x and the y and the a, but also the dx dt, the dy dt, and the dA dt, the rates at which the length and the width and the area were all changing. So that's kind of the idea with these related rates problems. It'll give certain information, and then it'll ask, well, if based on this, how fast is such and such changing? So what we need in that case is an initial equation that relates the quantities. In the original case, it was length, width, and area. We need a formula, an equation that relates those quantities. And then step 2 will be to differentiate both sides with respect to t, come up with a relationship between the rates, then input the given information, and hopefully that rate that it's looking for, how fast is such and such changing at a particular point in time, we'll have enough information to calculate that. So I've got another rectangle here. It's a rectangle, and it's not the area that we want, but it's the diagonal, the length of the diagonal of the rectangle. I think I've got a situation where I can paste it and write on it. Draw the picture. Picture is very important here. So let L, and I'm going to draw it a little differently here. Draw it like this. Be the length of the diagonal of a rectangle. So there's L, whose sides have lengths x and y. And assume that x and y vary with time. So it might get wider, it might get taller as time passes. If x increases at a constant rate of 0.5 feet per second. All right, when it says that, I know I finished in the middle of a sentence there, but if x increases at the rate of 0.5 feet per second, the bell, the whistle that's supposed to go off in your head at that point is to say, oh, that's dx dt. The rate at which x is changing with respect to time, it's told me the value, the numerical value of dx dt. Just like that. So you're thinking, okay, good, I've got that. Let's read on. Y decreases at a constant rate of 0.25 feet per second. Another bell, another whistle. It's told me the value of dy dt, the rate at which y is changing with respect to time. And because it says decreases, it means it's negative. So dy dt would be negative 0.25 feet per second. And then it asks the question, how fast is the size of the diagonal changing? The size of the diagonal, the length of the diagonal, I guess I should say, is L. The rate at which the diagonal is changing with respect to time could be denoted how? dl dt. dl dt. So it's asking us for dl dt. So what do we know? What do we need to know? We know x equals 5 feet. Let me scoot this over and I can probably summarize this a little bit better. X equals 5 feet, y equals 12 feet. dx dt equals 0.5 feet per second, and dy dt equals negative 0.25 feet per second. That's given information. It wants to know dl dt, and although it does not specifically give us the value of L, we can use the Pythagorean theorem and come up with the length of the current length of the diagonal. So what we need is what we ultimately need to find the final answer is an equation that relates all of these, basically x, y, dx dt, dy dt, L, and dl dt if necessary. Certainly it's got to have a dl dt in there, or dl dt in terms of everything else that's given. To get there, we need to begin with an equation that relates x, y, and L. Something without the derivatives, just plain old x, y, and L. And for that, that's the Pythagorean theorem. X squared plus y squared equals L squared. So begin there. Differentiate both sides with respect to t, and all of a sudden we've got an equation that has not only the x, y, and the L, but also the dx dt, the dy dt, and the dl dt. It's all in there, all 6 of them. And we know 5 out of 6. So that should be enough to find the value of, well, 4 out of 6. But we're about to know the length of the diagonal. and then that should be enough to find dl dt. So here we go. It's done here, so I'll talk through it. L squared equals x squared plus y squared. Differentiate both sides with respect to t, and use the power rule as it applies to the chain rule. The chain rule's in here because we're differentiating with respect to t, but none of the variables match the t. So there's the idea that L and x and y all somehow depend on they depend on t. They change when t changes. So the 2 comes out in front, 2L, and then we multiply by the derivative of L with respect to t. So it's 2L dl dt. And similarly, 2 comes out in front of the x, but we have to multiply by the derivative of x with respect to t, according to the chain rule. And then the 2 comes out in front of the y, but then we have to multiply by the derivative of y with respect to t. So we're looking at this equation, and it's good practice, I think, to figure out what it is that we don't know and solve the equation for that. That way, once it's just not a matter of substituting everything we know and then solving. Maybe solve it on the front end and then we substitute. You can do it either way, but I think it's neater and cleaner when we look at it like this. So all that has to be done there is to divide both sides by 2L. So you can see what I did. Divide that by 2L, divide that by 2L, and it looks like the right-hand side, and each term in the numerator has a factor of 2, the denominator has a factor of 2, so divide both the numerator and denominator by 2 and erase all the 2's, and it looks like this. And we substitute the given information into the numerator. Somewhere, if we know that this is 5 and this is 12, this is going to be the square root of whatever 5 squared plus 12 squared is. So the square root of 169 is 13. So that wasn't given, but that wasn't difficult either. So we come up with the length of the diagonal at that point in time. So substitute 5 feet per x and 0.5 feet per second for dx dt. 12 feet for y, negative 0.25 feet per second for dy dt. And then we get square feet per second. I don't know if I can attach any meaning to that because we're really not talking about area. But we would get negative 0.5 square feet per second in the numerator. Divide that by 13 feet. And then the feet in the denominator divide out one factor of feet in the numerator. And so we end up with feet per second, negative 0.03846 feet per second. I don't know that I would have guessed that the length of the diagonal was actually decreasing at that point in time, because x is increasing at a certain rate, but y, if they were both increasing, it would have been increasing for sure. But y is decreasing. Would you have guessed? What do you think?
I would have, because there's of course the limit set up to where it's usually longer if one side's far longer than the other. Mm-hmm. Because if you decrease the longest side without increasing the shorter side by a significant amount, then it's going to end up getting shorter until it gets to the point where it starts getting longer again because x is taking over the long side.
I mean, that sounds good to me. I think another way to look at it might be from in addition to the calculus perspective, there's the physics perspective, and I'm thinking if you could come up with a vector to indicate just where this point would go from where it currently is, and just look at the components. Where would it be? Who's had physics? You. Oh, okay. Maybe I shouldn't discuss the physics perspective. That's probably not going to shed any light on. How about the GeoGebra perspective? If we look at this, we've got time t equals 0, and as we let time begin to pass, the size and shape of the rectangle is going to change. And dx dt I've got set at 0.5 feet per second. So right now it's currently at 5, but after a second passes, we're going to let that be constant over the next few seconds. So it's going to increase by 0.5, by half a foot each second, and y is going to decrease by a quarter of a foot each second. Currently, is that what we got? Negative 0.035385. I think that's what we got. Yeah, that's what it was. As the values of x and y change, because dl dt depends on the values of x and y as well as the value of l, dl dt will change. So just consider what happens here as we let time pass a little bit. I mean, the length of the diagonal is decreasing because dl dt is negative, but dl dt,
Yeah, it's increasing, right?
well, L itself is decreasing,
Okay.
but dl dt is negative, so it causes L itself to decrease. I'm going to go back to 0 and do that again. So look at L. L goes from 13 down to 12 point something. So initially, L is decreasing because dl dt is negative. But dl dt is, it's going from, what, from, it's increasing. So at some point, dl dt gets to 0.
When x
And it-
equals y.
Yeah, that's an interesting observation. When I wonder what we could say there. There's probably some sort of proportion. What's 11.6 divided by 2?
It is
5.8?
Yeah.
It's 5.8. So what's kind of curious to me is the ratio of these two is 2 to 1. The ratio of these two is also 2 to 1, or 1 to 2, depending on how you look at it. So, there's probably something there. But at that point, when dl dt is no longer negative, L is no longer decreasing, and in fact, if we let time continue to pass, the length of the diagonal is going to increase as the seconds tick away. As the seconds tick away, and well, at some point when what the value of y gets to 0, if we then say we don't have a rectangle anymore, then maybe we should stop it at that point. But yeah, there's some other observations that can be made there, and you can let's see. I thought I had the animation turned on. There we go. You can kind of let it run, and you get that, and you see that dl dt is positive and it's increasing, so the rate at which L is increasing. Probably enough to say about it. I have one more of these for the next example. I thought I did maybe for the airplane problem. But we feel okay with example 2. So let's set that up. Basically, the relationship among the variables. Differentiate both sides with respect to t. Then you have a relationship that includes not only the variables, but also the rates at which the variables are changing. That's kind of the plan for all the examples in this section. An aircraft is flying horizontally at a constant height of 4,000 feet above the ground, and it's moving away from a fixed observation point on the ground. So here's a fixed observation point on the ground, and let's say this is ground level, and 4,000 feet above ground level. I'm not going to attempt to draw an airplane here, maybe just a dot. 4,000 feet above ground level looks like that. 4,000. And at a certain instant, the angle of elevation, theta, to the aircraft is 30 degrees. I'm just going to say theta. It's usually a really good idea not to put any numbers too soon. Wait until you've differentiated both sides with respect to t before you input any numbers. Otherwise, you put in numbers, you get constants, you differentiate, you get 0, and it doesn't help. So don't substitute any numbers that are given until after you differentiate both sides with respect to t. So the plane's going this way. And let's see, at a certain instant, the angle is 30, and the speed of the aircraft is 440 feet per second. I like to think in terms of feet per second rather than miles per hour because I was given the height in terms of feet, so keep the units consistent. How is theta changing at this instant? To express the result in units of degrees per second. Well, the quantity that we're given there the speed of the aircraft, 440 feet per second, I'd like to be able to say that's the rate at which something is changing with respect to time. What is changing with respect to time at the rate of 440 feet per second? dx dt, we could say dx dt is 440 feet per second. I guess my question would be, what's x? See, the airplane's going like this, so it'd be some quantity that's parallel to the direction of the. So I'm going to say this is x right here. We may not initially need it. We might not need that. But let a second go by, and we would expect, in fact, we would know that it's going to be 4,440 feet. And then another second go by, it'd be 4,880 feet. So x, the distance, the horizontal distance between the observation point and the airplane along the ground, parallel to the ground, is increasing at the rate of 440 feet per second. So if that's x, then dx dt equals 440, goodness gracious. There we go. Feet per second.
Now, Mr. Mondell, could we use our trig to find what x is?
At 30 degrees. Absolutely, yes. And we may actually need to do that. If not in the A part, maybe the B part. Maybe both. Maybe both. But we'll certainly do that. Definitely we're going to use the trig to set up a relationship among the 4,000, which is constant, and the angle theta, and the value of x. So we need something to give us the rate at which theta is changing with respect to time. So we have the side opposite, theta, and we have the side adjacent, theta. You're right, we're going to need the value of x. We sure are, because we need to know that. The side adjacent, theta, so what function is that? Trig function? Tangent. So the tangent of theta equals 4,000 feet divided by x. Side opposite divided by side adjacent. And what we need, since we know dx dt and we know theta, what we need is a relationship between d theta dt, or among d theta dt and the others, the x and the dx dt and the specific value of theta. So theta is 30 degrees. Let's go ahead and calculate x when it's 30 degrees. So what would that be? Tangent of 30 degrees equals 4,000 divided by x. X equals 4,000 divided by tangent of 30 degrees. Well, it's a 30, 60, 90 right triangle, but let's pretend like we don't notice that. Tangent of 30 degrees, I want to say is the square root of 3 over 3. Does that sound right? Square root of 3 over 3. So 6, 9, 2, 6, 9, 2, 8. 0.2. 0.2? Okay, feet. So x is 6928.2 feet. dx dt equals 440 feet per second. And what we don't know, and what we need to know, is d theta dt. So with a view toward coming up with a relationship, an equation that has a theta, an x, a dx dt, and a d theta dt, we're going to take this equation that we have and differentiate both sides with respect to t. Now, to use the power rule, I probably want to think of this as 4,000 x to the negative 1 to do that. So here goes. It's ddt of tangent theta equals ddt of 4,000 feet x to the negative 1. So we differentiate tangent theta, derivative of tangent of something is secant squared of that something times the derivative of that something with respect to t in this case. And on the right hand side, derivative of 4,000 times x to the negative 1 is going to be negative 4,000, well, feet, times x to the negative 2, but the x and the t don't match, so I have to multiply by the derivative of x with respect to t, dx dt. And we welcome the opportunity to do that because somehow we need to incorporate the fact that we know dx dt is 440 feet per second. The unknown is d theta dt. So I'd like to solve this equation for d theta dt. You can multiply both sides by cosine squared theta. And that would do it, I think. So let's see, d theta dt equals cosine squared theta times negative 4,000 feet over x squared times dx dt. And we know theta, we know x, we know dx dt. So if you substitute this information in here, it should give us d theta dt. Now, when it gives us d theta dt, it will be in radians per second. Radians per unit of time. And the unit of time here is seconds. So if we want that in degrees per second, we'd have to convert. So d theta dt. And if I had a little bit more room, I could be a little bit more careful. D theta dt at the specific value, I'm going to be more careful even though I don't have more room. Theta equals 30 degrees. And dx dt equals 440 feet per second. And x equals 6,928.2 feet. I don't have room to put all that in there, so I'm going to be cavalier. Cosine squared of 30 degrees. So I can use degrees there so long as my calculator is in degree mode. If my calculator is in radian mode and I want to use radians, I can go with pi over 6 radians. But I can use degrees if my calculator is in degree mode. Times negative 4,000 feet over 6,928.2 feet. But we got to square those feet as well as squaring the 6,928.2 times dx dt. And dx dt is 440 feet per second.
Where did the 6,000 come from?
It was up here.
It wasn't x squared before?
Well, I've got it squared right here. Squared right there. So it boils down to a calculator problem. Let me just inspect the units and make sure they sort of make sense. If we multiply these feet by these feet, we get square feet per second. But we have square feet in the denominator. So the square feet in the numerator divide out with the square feet in the denominator, so it's just per second. What per second? Well, radians per second. Radians per second is going to be the units. So I could try to punch this up and let's see what we get. Maybe you've already done it. Check to see what mode my calculator's in. It's in degree mode. So I should be able to do this. So cosine of 30 and square that. Hopefully we'll take the cosine first before squaring. Times negative 4,000 times 440 divided by 6,928.2. Well, I probably should have if it had been anything more complicated than just the number itself. It would have been smart to put that in parentheses, but since it's just the number itself, I think I'll get by with it this time. As a rule, it's really good to,
operation.
yeah, it's good to close that in parentheses. Anybody get this? Negative 0.0275 radians per second. Negative 0.0275.
So we got even less than that for like 5 feet per second.
So to convert to degrees per second, we'd need to multiply by,
5 over 180.
well, I'm thinking in this case 180 over pi. It's kind of like need to multiply by about 57,
Oh, right.
and then we'll have degrees per second times 180 divided by pi. So negative 1.58 degrees per second. That's what we're looking at. Does it make sense that it's negative? Angle's getting smaller. Yeah. If the airplane goes, then the angle of depression is diminishing. So at least we feel like we got the sign right. Negative. An interesting thing, I think, in all these related problems, every last one of them, if we have a small enough unit of time, maybe a second, in some cases a minute is a small enough unit of time, depending if things are changing very slowly. Let a second go by and go with our assumptions. Just let a second go by and recalculate using basic trigonometry. Suppose the airplane is 4,440 feet away from us horizontally. We could use trigonometry and calculate the value of x, and we could see and do an inverse tangent and find the new value of theta, and hopefully it's about 1.5 degrees less than 30 degrees. I don't know if I want to take the time to do it because a little bit more going on here, but we could do that. Now there was another one I did. It's been honestly at least 5 days since I've looked at this, so I don't know if I even finished it, but I'm going to try to open it. No, don't say. What would this be? Airplane? Would that be a good name for it? Airplane.
Looks about right.
All right, maybe. That looks about right. So 30 degrees. If we let us, and look at the vitals here, negative 1.57. So either I can't say that these have been done independently because they've been done by the same person, just at different times. So if I missed it, at least I missed it exactly the same way both times. But negative 1.57 something degrees per second is what we're looking at, d theta dt. If we let a second tick by, we would expect theta to go down to about 28.45, something like that. So let's let a second tick by and see what happens. Yeah, something like that. And I don't know if I can make the spreadsheet any bigger. Maybe make that a little bit bigger. Okay. So that's kind of what happens there. So it's decreasing. And notice, as time passes, what happens to d theta dt? As time passes, the angle is still decreasing, but the rate at which it is decreasing is decreasing, yeah. So it decreases more and more slowly the farther the airplane is from the initial point. So there we go. And I may be able to refer to that for the B part as well. Hopefully we can use some of what we've done for the B part. B part, how fast is the distance between the aircraft and the observation point changing at this instant? Distance between the aircraft and the observation point. So that's the length of that diagonal. We could call that L, I suppose, if you want to. How fast is that changing at this instant? And express that in feet per second. So to use the picture that we had, if we call this L, then we're looking for dl dt. Well, we could calculate the value of L. This is a 30, 60, 90 right triangle. So I believe the length of the hypotenuse is twice the length of the side opposite the 30-degree angle. We could use the sine function to do this, but because sine of 30 degrees is 1/2, I think we can show that L is 8
8,000 feet. So L equals 8,000 feet. And we need a relationship among the quantities x and L, because we need a relationship between dx dt and dl dt, because we know dx dt, and we know L, but we just need to know dl dt. So see if this makes sense. X squared plus 4,000 feet squared equals L squared. I think this would work. It relates X and L. So if we differentiate both sides with respect to t, we'll have an equation that relates X, L, dx dt, those three we all know, and the other one would be dl dt, the unknown. So ddt of x squared plus ddt of this constant, 4,000 feet, what's that, 16 million square feet? Well, the derivative of 16 million square feet is still just 0. Equals ddt of L squared. So 2x dx dt plus 0 equals 2L dl dt. So solve it for dl dt, because that's what we need to know. dl dt equals 2x over 2L dl dt, 2x over 2L dx dt. If I divide both sides by L, by 2L. And so it looks like dl dt equals x over L dx dt. So if L equals 8,000 and X equals 6928.2, 6928.2 feet, and dx dt equals 440 feet per second, then dl dt equals 6928.2 feet over 8,000 feet times 440 feet per second. What about what's dl dt? .1 maybe feet per second.
It's getting that much longer every second.
Yes, the length of the diagonal is increasing by 381.01 feet each second. Moving back to this picture maybe. So at t equals 0, yeah, there's dl dt, 381.05. So if we let a second go by, we would expect the value of L to be approximately what? 8,381. Now, if the rate at which L is increasing is decreasing, it'll be a little less than that. And if the rate at which L is increasing, it'll be a little bit more than that. So let's let a second go by and compare to 381.05. Okay, it looks like dl dt is actually increasing. So where's the second? I don't have to use that. I can use this. Not a whole lot better, but maybe. Come on, 1 second. There we go. So I need an input box. So yeah, but it looks like the rate at which L is increasing is increasing. Any explanations for that?
Kind of like I said before, I guess the bigger the difference in side lengths, the more significant an increase in the longer ones.
Bigger the difference in.
If X is way bigger than Y, then a smaller change in X will result in a greater change in the hypotenuse than if it was X and Y similar.
Does X even change?
See the height. Yeah, X changes basically, and basically, let me see if I can
Yeah,
do
Y
that.
is smaller than X relatively speaking.
Well, I guess we can compare this picture to what? Let's go out here and draw this one. Ooh, wow, that's rough. There we go. So we look at this, and the horizontal speed parallel to the ground is constant, so we're assuming it's constant, over an extended time interval. So as we if we increase X by a little bit, by this much, then the diagonal we would expect to increase by maybe that much at that point. But if we increase it by
Doesn't make sense.
this is counter to what I'm thinking. I thought I had it, but then I don't have it. Increase it by that much. I want to think in terms of. I want to describe in terms of vectors, but I don't think that's a good idea.
Could you say that as the difference grows, it moves closer to hypotenuse equals Y?
I think it has to do with as it goes more and more horizontal, the component in the direction of the actual change is greater as time passes. We could look at it algebraically as well, but I don't think we have time. Let's look at example 4. If it becomes necessary for you to take a break, feel free to do so, but I have to dismiss a little early today because I have a meeting to go to. And it will be significantly early today, at least. I like to get out of here by the time the big hand reaches 11. So I'm going to skip the break today. If you need to take a break, take a break, but I'm going to press on. A conical tank. I don't know why anybody would want to store stuff in a conical tank, but maybe there are good reasons for doing it. Makes for a great calculus problem, though. A conical tank with vertex down.
Maybe that's like a funnel and you can open it at the bottom.
Okay, I'll go with that.
Like one of those light bulbs you can put in a pot.
Yeah, that would work.
Stab it in there and it's got
That would work.
a halogen bulb.
It's got
the storage stuff.
kind of a smaller one there, but there are probably good reasons for doing it. Vertex down has a radius of 4 feet at the top. 4 feet right there. And we're going to say, I guess, maybe I should say circular. It's a circular conical tank. So the top there, any cross section perpendicular to the axis is going to be a circle. So that's circular, and cross section there is also going to be circular. So a conical tank with vertex down has a radius of 4 feet at the top and is 10 feet high. So 10 feet from there down to there, or up to there. 10 feet. If a fluid flows into the tank, my faucet drawing skills are a little weak. So what? How can I depict a fluid flowing into the tank? Just
a water machine.
Like a little elbow pipe.
that looks kind of rough there.
Little paper cups.
Paper cups.
Yeah, I guess you could send it in like paper cups.
I'm going to attempt to draw a faucet. This could be dangerous. Am I going to? No, it's good. Should I think about it? Maybe I'll tell it.
You already started.
So a fluid. There's the fluid. That's the direction of the fluid. It flows into the tank at a radius of 4. Let's see. At a what? At a rate of what? 8 cubic feet per minute. There we go. How fast is the depth of the fluid increasing? So it gets deeper as more and more fluid accumulates. So how fast is the depth increasing at the particular point in time when it's 6 feet deep? Okay. So we want to know what is, well, we need something to, need a variable to represent the depth. I don't think I want to use D. ddt is probably going to be problematic. We could use capital D maybe, and it'd be okay.
L sounds good.
L for depth?
B.
V for volume.
V. Well, we're going to use V. V, in fact, what we know here, the volume is dVdt. The rate at which, well, the volume is V. The rate at which the volume is increasing would be dVdt, or changing, and the volume is increasing at the rate of 8 cubic feet per meter. So the V is kind of taken.
Per minute, right?
Per minute? Did I say per second?
Like
I'm sorry.
the benthic zone in a lake. It's like the depth of the lake benthic. B.
B? Capital? Can we use capital B?
Jabber.
Let's just do it like
LB.
LBJ.
LBJ. Could I call it Y since it's arranged vertically? I'm going to call it Y. Let that be the depth. So it's Y. That represents the vertical depth from there to however deep it is. Okay. We need a relationship among the variables Y and V so that we can differentiate both sides with respect to T and have a relationship among the quantities Y and dVdt, since we know Y equals 6 at this point in time. It's a little tricky to express the volume in terms of just Y, though, because what's the formula for the volume of a right circular cone? Anybody know? I want to say maybe 1/3. 1/3 time 1/3 pi r squared times the height.
How do I know this?
What math?
Well, we don't really do all that in college algebra. Yeah, where would you be expected to have picked this up? Maybe on the street somewhere. I'm not sure.
Oh yeah, we talk about this on the street all the time.
Technically, there is a
Trigonometry?
section in Algebra 2.
Technically in
I don't
algebra
remember it,
2,
but
where you
I
do
know
volumes of
We
3D
go like
figures.
conic sections.
Yeah, we do a conic section.
Conic sections, maybe. You might have seen this. So, okay, basically 1/3 pi r squared, the area of the top there, times the height. It's exactly 1/3 of the volume of the corresponding right circular cylinder. But anyway, 1/3 pi r squared times the height is the volume. So we've got the Y there, but we need to express the volume in terms of the depth. Volume in terms of the depth. So let's think about this. It's similar triangle time. So the ratio of I'm going to call this little r. So we kind of need that to calculate the volume. We need r, we need y, and then that would, y is the value of h. So we could do this. So what's the ratio of r to y? For this particular right circular cone, it's always equal to what? Maybe put the y right here. R is to y as 4 is to what?
4 is to 10.
4 is to 10. Because the entire tank is 10 feet. So R is to y is 4 is to 10. So we could express r in terms of y and use that to eliminate the r from the equation. Because we'd like to have the volume strictly in terms of the depth, because the depth is what we know. So how about r equals 4/10 y, or r equals 2/5 y? So for this particular right circular cone, not every right circular cone, but this particular right circular cone, v equals 1/3 pi times 2/5 y quantity squared times
Is the height 10?
the height is y. The height is y.
Oh, okay.
That's what we decided on after much discussion. The height is y. So r is 2/5 of y, and h is equal to y. So for any particular depth, this quantity is going to be 2/5 of this quantity. So we've got y, and then we've got 2/5 of y right there. 2/5 y. And we substitute them into the formula, and then we have an equation that relates the volume and the depth. You tell me the depth, I just punch it in here for y, and it'll calculate the volume for us. With this in mind, we can differentiate both sides with respect to t and come up with a relationship between the rate at which the volume is changing with respect to time and the rate at which the depth is changing with respect to time. Simplify a little bit first. V equals 1/3 pi times 4/25 y squared times y. So v equals 1/3 pi. Well, why don't we say 4/75? 4/75 pi y cubed. So this formula doesn't work for every right circular cone, but for this one, because the ratio of radius to depth is 4:10, it works for this one. dv dt then, or let's say ddt of v equals ddt of 4/75 pi y cubed, so dv dt equals 4/75 pi is a constant, so we can take that out there, 4/75 pi, and then multiply that by 3y squared dy dt. Divide the 3 into 75, 3 goes 25 times into 75, and we have this, dv dt equals 4/25 pi y squared dy dt. And we want to know how fast is y changing when we know everything else. When we know y equals 6 feet, when we know dv dt equals 8 cubic feet per minute, we want to know how fast is y changing. So I'm going to solve it for dy dt. So dv dt, I'm going to multiply both sides by 25 over 4 pi, 25 over 4 pi y squared. Will that do it? Or you could multiply both sides by 25, divide both sides by 4, divide both sides by pi, divide both sides by y squared. And I think you get this. So dy dt, with the given information, is going to be 25 over 4 pi times 6 feet, square that, and then multiply by 8 cubic feet per minute. We're going to have feet cubed in the numerator. We're going to have square feet in the denominator. So we'll end up with feet in the numerator per minute in the denominator. So it would make sense if we wanted to, how fast is the water level rising? So many feet per minute. So at least the units make sense. Hopefully we get the correct number to go with those units. Ooh, not the eraser. I left the UI there. So this is going to be about, now I had to be real careful with this, 25 times the 8 divided by 4 divided by pi not loving the new operating system, divided by pi, come on pi, divided by 6 squared. Not use for that exponent.
So you could just put those in parentheses and it'd be the same thing, right?
Yes.
Okay.
Just put the 4 times pi times 6 squared all in parentheses. Divide by that quantity. And hopefully we all get this. Did you get that? 0.442 feet per minute. Right. So what we'd expect if we let a minute go by, if the rate's not changing dramatically over that time span, if we let a minute go by, we would expect that whatever the volume is, we would expect that whatever the height is, 6 feet, if we let a minute go by, a minute later it would be about 6.4 something feet. And I would guess a little bit less than 6.442, because as it gets deeper, the rate at which it's getting deeper is diminishing, because there's more space to fill as that radius increases, as the circumference, I guess, area increases as we get higher. So I would say a minute later it'll be less than 6.442 feet. But that's the idea. You can do the calculation and check it, but don't have a GeoGebra one for this one. Oh, that's the last one of that section. So move on. There are some good, I'm going to do a different approach with the homework. The homework has not been posted yet, but you still have the 3.7 problems to work on. So if you're looking for something to do between now and Wednesday, you have a lot of these related rates problems from section 3.7, 8 of them. A lot of good ones. Some of my favorites are the conical tanks and the grain pouring from a chute forming a shape of a cone as it lands. Kind of an interesting type problem. So there's several to practice on. I think for the ones in chapter 4, I may just give you some problems out of the book. I think I can give you a few more. I may or may not have time to work through those problems to get you solutions to them. But big odd-numbered problems, you have solutions manuals? No? Well, maybe I'll try to work as many of them as I can, but I think that might be a fairly good approach, maybe a better approach than what I've been doing. So that's kind of the plan. Let's look at 4.1 and see what are we going to be talking about in Chapter 4. Chapter 4, we look at functions, at graphs of functions. We'll be analyzing the graph of the first derivative and trying to come up with what are some key features of the first derivative that give us information about specific aspects of the graph of the original function. What are some key features of the graph of the second derivative that give us specific information about key features of the graph of the original function? How's the original function behaving if we have knowledge of the graph of the first derivative and the graph of the second derivative? Some of that will be with a view toward answering the questions that are posed in section 4.1. So we begin talking about, see at the top, the title of the section is extrema on an interval. Well, let's look and see what these extrema actually are. and look to see if we have a closed interval and a continuous function, how an extremum may be found.
If you hit close, it'll just open itself back up with Windows Explorer.
All right. So I
Actually,
really want
you
to
almost always have to hit cancel on it.
Oh,
Yeah, there it goes.
so hopefully that'll be there when I get back. Shrink that a little bit. A lot of different pictures one might draw for a situation like this. I'm going to try to draw something that's somewhat generic, but not nearly as much as probably it should be. Function f is said to have an absolute maximum on an interval I at the point x sub 0. Well, the interval I is not necessarily an open interval, and it doesn't necessarily happen in the interior, but let's see, if we had something like, I mean, a typical example might be something like that. X sub 0. And let's see if this fits the condition. On an interval I, maybe this is our interval I. If f of x sub 0, well, what's f of x sub 0 right there? F of x sub 0 is the largest value of f on the interval. Visually, it's the highest point on the graph within the interval. Now, notice the or equal to bar there. There's a situation, we probably won't run into it unless we're just getting really nitpicky about terminology and things like that. But technically, if we have a function that's constant on an interval, then every number in that domain would be the location of an absolute maximum. Because pick a point, any point on there, it's the highest point on the graph in that interval, in as much as there's not one that's higher. Now, there might not be one that's lower either. But if there's not one that's higher, everyone qualifies as the lowest point, and I guess everyone qualifies as the, well, everyone qualifies as the highest and the lowest simultaneously. But this is a more common situation that we'll encounter. F of x sub 0 is the largest value, so the function has an absolute maximum at that value. And similarly, if we have something like that, and an x sub 0 there, and if we evaluate the function at x sub 0, and that's the least value of the function on the interval in the sense that there's nothing in the interval, no number in the interval where you evaluate f and you get a lesser value, then that's an absolute minimum. F has an absolute minimum at that particular point. In either case, collectively they're referred to as absolute extrema. Individually, you could say absolute. It has an absolute extremum, just to save time from saying minimum or maximum. Then we have a theorem. The extreme value theorem. Let's consider the hypotheses. If a function is continuous, moderately strong condition, continuous on a finite, I would say maybe, I'm sure that I got the word finite from the textbook, but in terms of finite, it means bounded. It doesn't go off to infinity one way or the other. The measure of it is finite, probably I should say. The number of points in the interval is not finite, but the measure of the length of the interval is finite. So if f is continuous on a finite closed interval, AB, then f has both an absolute maximum and an absolute minimum on that interval. If we lose the continuity, it might not have either one. If we lose the closedness of it, then it might not have an absolute maximum or an absolute minimum. But if it's a continuous function defined on a closed interval, it has at least one of each. So there's A, and there's B, and the function has to be defined at A somewhere. It can be greater or less or the same at B. Let's say it's right there. I could connect the dots with a straight line segment. I could go up above, down below. It could wiggle around a lot. But if it's continuous, on this closed interval, it will have both an absolute maximum and an absolute minimum. What if I just do that? Where would you go looking for an absolute maximum? Maybe right there is where we find an absolute maximum. Like f of x sub 0 is the absolute maximum. And where would you go looking for an absolute minimum? A. So x sub 1, f of x sub 1 is the absolute minimum. So in this picture, it could happen at an endpoint, or it could happen at a point in the interior of the interval. It could happen multiple times. If it takes on the highest value and then dips down from that, it takes on the highest value again. But we've seen an example of that with a horizontal line. So it could have multiple absolute extrema in the interval. If I lose the continuity, all sorts of things can happen. If I didn't want it to have an absolute maximum, I could do this. And then maybe it's got to be defined on the interval, just not necessarily continuous. And if I didn't want it to have an absolute minimum, I could do something like, oops, I want to fail the vertical line test. Let's say it won't. Something like that.
Wouldn't be the point like right before the hole?
So that's the thing. That's beautiful the way you said that. The point right before the hole in the graph. What point would that be?
Limit.
Say the hole in the graph happens at x sub 0. X sub 0 minus how much?
Yeah.
And that's the critical, I guess, question or the observation to make, is that because of the way the real numbers are ordered, you go to the left a little bit, but as soon as you step to the left a little bit, there's something in between that's going to be a little greater than what that was based on the way this is set up. Yeah.
You just write it as x equals limit as x approaches b from the left.
Well, you could say that the limit exists, but the limit would be this value. But since that's not the function value, the limit does exist, and I've kind of drawn the picture that way. But since that's not the function value, it doesn't qualify as the maximum value on the interval. The function doesn't actually take on that value because of the open circle.
Yeah, that's why you would say limit.
Right.
Basically, the closest you can get with whatever you're doing.
Right. And the limit does exist, but it doesn't make it the maximum value of the function. It's maybe the least upper bound. It would be an upper bound for the function, and the least such. But if the function doesn't take on that value, it's not the maximum value in the interval.
Yeah, I thought that was the purpose of limits, though, so you could notate things like that.
Yeah, but we could go back to the definition, I suppose. What is f of x sub 0? F of x sub 0 is this. And that's not the maximum because they're higher values just to the left of that. So it's not f of x sub 0, it's not a little less than f of x sub 0. So you go a little to the left of f of x sub 0, and they're points higher than that. Right? So it doesn't have a maximum value. And similarly, it doesn't have a minimum value. The lowest the graph goes, well, can I say that? How low does the graph go? Whatever this value is right here, f of b, not f of b, whatever the y-coordinate, whatever the value of the limit is, yes, whatever the value of the limit, as we approach b from the left, that's going to be a lower bound, and it's going to be it's going to be the greatest lower bound but it's not, the function doesn't take on that value. So there is no least value of the function on this interval. No maximum or minimum. If we lose the continuity, then we lose the result of the theorem. Yeah? All right. So if it's continuous, or what if we keep the continuity, but we lose the closedness of the interval? Well, what if
It's a closed interval with an extra dot above the count.
Imagine, well, heck, imagine this. Yeah, keep it simple. I was thinking vertical asymptotes, but no, we don't have to go there. Keep it simple. Just connect those two line segments to those open circles. What's the maximum value of the function on that interval?
That one.
Well, if we evaluate the limit as x approaches b from the left, we get this y value, whatever it is, but the function never gets there. Scoot a little bit to the left, it goes higher than that. Yeah. If we take the limit as x approaches a from the right, we get this function value. That's less than any function value on the interval, but the function never gets that low. If we scoot just a little bit to the right, and look at that, oh, but wait, it goes lower than that. So, no greatest value, no maximum value, no minimum value on this interval. So it's defined, and it's continuous on the interval, but it's not closed. Got to have those endpoints in order to reach the conclusion. I almost felt like math there for a minute. Yeah.
Makes sense.
All right.
Can we do like x squared?
X squared on what interval?
Just like when it's infinity?
Yeah?
Yeah.
What, like on the set of all real numbers?
Yeah.
Or we could. Now, it could be that the function, I'm not sure where you're going with this, but I can guess. It could be that the function has both a maximum and a minimum, even though the interval's not closed.
Okay.
It doesn't have to be closed to have a maximum and a minimum. It's just we lose the guarantee
Okay.
if it's not closed.
Because we wouldn't know the maximum if it was just x squared.
Yeah,
With
the
no
maximum
input,
is
because it's
positive infinity.
Definitely going up.
Right.
Minimum is 0.
Would it be infinity? Would that be the maximum?
You would say it doesn't have one.
Okay.
But just for y equals x squared on the interval negative infinity to positive infinity, well, it's not a I guess what? It's not a finite closed interval because it goes infinitely
Well, it's not a
far.
closed interval.
And well, there's some weird ways to define closed
Anything
from
with infinity has to be
topology.
parentheses, though, right?
Right. Yeah, we probably shouldn't
Be an open
have
interval.
that discussion because there's some intervals. Strangely enough, I should just zip and say no more about that because we just don't go there until several math classes from now. But yeah, y equals x squared, negative infinity, positive infinity would have a minimum, but no maximum.
Kind of like when they told us they couldn't have negative numbers in 7th grade.
I might have missed that day. I've got to stop there if I'm going to make my meeting.